My presentation is going to be about use of the Riegl VMX 250 on very long tunnel precise surveying. Everybody can start to think, oh, it's going to be done without GPS inside such a long tunnel. Well, one of our clients asked us for the possibility of surveying two parallel tunnels in northern Spain for the future high-speed railway line between the Leon state and Asturias state. These tunnels are finishing soon and are the second longest tunnels in railways tunnels in Spain. At the moment, the 6th in Europe and the 7th in the world. We can see here just a bit of the geography of the place. It's quite mountainous. Here is a projection of the Google Earth surface of the tunnel alignment. You can see pretty heavy topography. So the main characteristics of these tunnels, and there are two single-track tunnels with twice 25 kilometers. They have a longitudinal gradient of around 17,000, a circular section of 8.5 meters diameter. They have every 400 meters connecting galleries as well. They are 50 meters apart, the two axes of these two tunnels. This project can be divided in two parts, mainly the north side with the two parallel 15-kilometer sections, and the south part with twice 10 kilometers. They're actually being built by two companies, the north side and the south side, independently. There is also an auxiliary access tunnel with 2 kilometers long. You can see it there. Well, our partner in Spain and the client asked for 3D laser scanning of the tunnel. And, well, 50 kilometers of tunnels and not yet finished. That means with works and jobs going on. And they asked for 2 centimeters accuracy, absolute accuracy, on their internal network, survey network. And we knew there is lots of problems regarding the availability of survey teams inside the tunnel, because there is many companies working at the same time. There was also problems regarding air quality and oxygen. Pretty often the tunnel should be the work stopped and people must get out regarding the lack of oxygen or other issues as well. And our concern was also the cost and the time that would be done by terrestrial laser scanning. So we started to think about using our Riegl VMX 250 on such a long tunnel. So the first thing we thought about was how could we get these accuracies of 2 centimeters with such a long lack of GPS observations inside the tunnels, so the navigation would be only based on inertial measurements and the DMI. So we decided to make a test near our office in Portugal, in Coimbra, where we have a road, so we use this road as a test field for this mobile scanning, for our mobile scanning system, where we have a set of regular high accuracy control points, and where we could evaluate, again, like my former two colleagues, planning is very important. And how could we get these precisions? We knew there is a new possibility on reprocess regarding the flexibility of the data, of the trajectory, regarding control points, and allowing to adjust better this data to regular control points. So we decided to make this evaluation project simulating a long tunnel. We didn't have such a long tunnel near home, so we decided to do it just by simply disconnecting the GPS antenna on our system. So we had this road, it's 2.5 kilometers long. We can turn around on cycles, making each cycle around 5 kilometers. And so we just performed a normal mobile laser scanning project with the difference that after the normal and good initialization, we just make a short stop, disconnected the GPS antenna, and went on cycles until we acquired these 25 kilometers, and finishing again with GPS, and as usual, with a 5-minute stop. To evaluate the accuracy and this possibility of control points, we had also a very good data set from the same stretch of road in normal conditions, with good GPS conditions, and with several quite dense control points. So we knew we have this good data set of mobile laser scanning from this road, and we use the other one without GPS and with some control points, and we would evaluate the frequency of these control points to allow this new data to be as close as possible to the other data with GPS. And after several analyses, we saw that using 25 meters as cadency for a good control point, we could reach the 2 centimeters root mean square error. Another important issue was the materialization of these control points on the tunnel. The tunnel had quite amounts of water in the ground, so we could not use control points on the ground. We had to go to the walls. And what would be the best form or shape to use these control points? We decided for squares, 25 centimeters wide, and always the same corner to be surveyed by total stations. The acquisition was done within 20 to 25 kilometers an hour, and we can see there the mean distance to the scanners of the walls of the tunnels were 4 meters, assuring circa 9 scanning lines each square, each control point, to be visible on the data. So we have, as most important constraints, very long GPS signal outage, short time window for the operation as well. Driving conditions inside the tunnel were not sometimes the easiest, and we could not enter one side and leave the other because there was an interruption in the middle of the tunnel, so we have to turn back. And we have to divide this survey at the end in 3 different projects, in 3 different months actually, doing to the works going on. So we took all these missions between September and January this year, and yeah, I can tell it was a hell of a job on our office using control points and to get all the data corrected. But before that, I want to show here some interesting things.